This is Parametric podcast number 46, and today we're talking about pistol shrimps. So that's right, there's a shrimp out there called a pistol shrimp, and what these shrimps do is that they can shoot a jet of water, which then collapses on itself into vapor and then making a cavitation. This cavitation has a really high pressure that then stuns its prey. So in other words, it shoots from the hip and then eats its prey. So that's pretty cool. And to do that, we're going to look at a paper called Unveiling the Physical Mechanism Behind Pistol Shrimp Cavitation. And for those of you who haven't seen this, check out this video that I've just put in the card above. This takes you to National Geographic and they show you a little video of this pistol shrimp in action. It's really cool. They come back here and watch the rest of this podcast. Okay, so I assume you've seen that video. And I think we can all agree that that's quite amazing. So you saw the claw, how it cocked, and then it released it and it fired this invisible jet effectively. You can't really see it. It hit the other shrimp, it killed the shrimp, and now it can eat it. And so how does that work? So it's not just hydrodynamics, it's also aerodynamics. And it takes advantage of something called cavitation. Cavitation is this phenomenon where when you have a high enough pressure, you can then create water vapor. And then this will then create these bubbles. Sorry, I mean, it's low pressure, which then vaporizes, which creates these bubbles, and then they collapse on themselves, creating high pressure. And this high pressure is so great, it's so massive, like me, that it can take out bits of metal. Like if you look at ships and submarines and whatever, especially if they're like 10 or 20 years old, you look at their propellers, you look at this, you can see these dents coming out of them. That's from cavitation. These bubbles that are formed due to low pressure have now collapsed on themselves, and there's so much pressure involved in that that it actually takes bits of metal off of the object. And the pistol shrimp uses this to its advantage to be able to stun its prey. So let's look into how this works with this paper. It's open access, so you can find it in the link in the description. And while you're at it, make sure to like, subscribe, and share this with your buddies. Okay, so the snapping shrimp, as they call them, pistol shrimps or snapping shrimps, they use a specially shaped claw. So we saw that in the video where one pincer was a little bit differently shaped to the other pincer. One of the pincers has this cavity in it. The other pincer has this little hammer-like structure. And then when it snaps shut, the hammer goes into the cavity. It shoots water out of the special hole, like a specific hole that it has. And then that creates this phenomenon here. And we'll talk about that. They use simulations to show that during the claw closure, this high velocity jet forms and it induces a vortex roll up around it. And if the speed is high enough, the intensity of this vortex motion is so strong that it can depressurize the vortex core, leading to vaporization of water, and then that leads to cavitation. And this cavitation collapses and creates high pressure. And they say that cavitation is a very effective way of generating shocks. And it doesn't just occur on these pistol shrimp. As I said, it can occur on like ships and submarines, but it can also occur on regular animals such as dolphins. And they say here that dolphins cannot swim faster than 15 meters per second due to cavitation formation on their flippers, which causes pain for them. On the other hand, there are other animals out there, such as the mantis shrimp. They have two hammer-like or club-like appendages. And when they strike them together to kill their prey or stun their prey, that also creates cavitation sometimes, but that's an unwanted effect because that damages their claws. Whereas the pistol shrimp, on the other hand, it seems to be the only animal that has evolved, at least as far as we know, that has evolved to have this specifically happen. Because even though the claws can get damaged, if one of the claws gets too damaged, it just sheds that and grows another one. It's pretty amazing. And they say that as I said, the claws are expendable. And interestingly, when, let's say, the larger claw is shed, the smaller claw will then grow to take the place of the large claw, and then it will grow the other side to fill in that small claw. So that's pretty amazing. And they say when the claw is fully opened, so when we saw in that video, it opened, the water obviously fills the socket because now there's a void there and the water rushes in. Then when the claw closes rapidly, the hammer, so the plunger bit, goes into that socket and then water expels, creating a vortex ring. in similar ways as an air vortex cannon. And they say that the claw is a very complex 3D shape. So instead of using a pistol shrimp's claw, they built a specific device for this. So those of you who can see the paper and are playing at home or watching this, you can see this device on the right here. And it's effectively, for those of you who can't see, it's just this on the bottom, you have a little perspex channel, and it's open on one end. Then on the top, you have a hammer, and then you can release the hammer into this perspex box from the top, and that makes all the water rush out. And this approximates the shrimp claw. And they say that the jet velocity has been estimated by other researchers to be 25 meters per second. Now, interestingly, they say that the pressure drop they think is about 300,000 pascals. So that's very high. Now, interestingly, they also say that other investigations have suggested that it can be as high as 2,000 bar, so 2 billion pascals. So not 2 million, 2 billion. That's really high. So obviously, it's a long range. In other words, what they're saying is they don't really know how high the pressure is. It's between very high and insanely high. And in this work, they're looking into a bit more how high that pressure is, and we'll find out later just how high it is. It's pretty mind-blowing. And they say that the cavitating flows are known to have a vast variation in speed of sounds from 0.01 meters per second for a liquid vapor mixture. So when you have the cavity forming, obviously you have a certain amount of water still in there and a certain amount of air. So that's this mixture, and the speed of sound can be very low, so 0.01 meters per second, or it can be very high, up to 1,000 meters per second if it's just pure liquid. And they say that the Reynolds number of the jet is about 4,000 based on its diameter. And then they have their results. So let's look into them a little bit before we read what happens. So in figure 2, we have, they say, the real life claw model that they used, and it's going through the closing process. And you can see that the vortices are shown with the velocity gradient second invariant. I just want to touch on this briefly. I'm not going to explain it completely because it's very intense in maths and you're probably going to get bored. But when you have a flow, I've mentioned this in other podcasts, that when you have vorticity, it doesn't necessarily mean that you have a vortex. And there are ways of determining whether you have a vortex or not. One way is called the Q criterion, which is what they say here, the velocity gradient second invariant, or the second invariant of the velocity gradient. And what this does is you can determine whether certain criteria are fulfilled, and if they are, then you know that there is a vortex there. The Q criterion is a very popular way. Another way is the lambda 2 method. I personally prefer the lambda 2 method. It's a little bit more complex in terms of math, but it's more robust. And then you can also use circulation. I like circulation as well because I've done a lot of work on airfoils, and we use circulation on airfoils a lot. So having circulation, vortices, it really is a nice intuitive way for me to think about it. But all these 3 ways are good, and there are other ways as well. Q criterion and lambda 2 are the most robust. So what they have here is the Q criterion plotted from 0 above. When you have anything above 0, you have a vortex forming. And you can see there are all these weird vortices forming through the initial closure stage. Then as you close through, the water shoots out of that hole, and they have this vortex ring forming. And notice it's not really circular. It's moving down as you go in time. So this last snapshot here, you can see the vortex ring is not really coherent anymore. It's just imploding on itself. And they talk about what happens. They say, as the plunger starts to move, flow detachment occurs, and 2 counter-rotating vortices form at the wake of the plunger, indicated with 1. So on the edges here, when the flow separates from the hammer, you have these vortices forming. They say, an attached vortex grows at the wall edge socket, and then due to the fluid being expelled through the socket cavity. And they say, because of the closure speed, the high-speed jet is expelled from the opening between the plunger and socket walls, and up to 30 meters per second. And that causes this vortex roll-up. And within this vortex roll-up, you have cavitation forming. So there's low pressure enough. So a vortex core is a very low pressure region. And so you have this vaporization occurring, and that's when you get cavitation. And then you get this imploding on itself, and that's when you get that high pressure. And let's go to figure 3 now. So this is what we started off with in the podcast. And you can see just how rectangular this vortex ring is as you shoot the fluid through the hole. Now that didn't sound right. Okay, let's move on. So you shoot the fluid through the hole, it creates a vortex ring, and then it stretches, and because the vorticity around this ring is impacting each other, so that's why you get this change in this structure. So it's imploding on itself, and then finally you have this not coherent structure. And they say that this rectangular shape is because of the channel is rectangular as well. And they say that its shape still resembles a rectangle later on, but it has smooth corners under the influence of viscosity. So these edges are being taken off of the corner of the vortex ring. And they say at 0.315 milliseconds, the vortex ring is completely detached and travels with the jet. And it gets elongated and finally approximates effectively two cylinders rotating around their axes, and then they implode. And then they have this other figure here, which is quite cool. Again, they have the Q criterion plotted, and they're showing the amount of cavitation. So whenever you see a black hashed region, that's when you have a vapor, they say a vapor volume fraction of 1% is that isosurface. So you can see as you start off, you have quite a big isosurface, and there's quite a lot of volume there. Then as you go with time, this isosurface starts to get smaller and smaller, which means that there's actually less volume which is being occupied by vapor. But because it's getting smaller, it's getting more concentrated. And then in this figure here, they show just how these vapor pockets evolve over time. So you have anywhere where there's this black line, this outline, you have the vapor constituent is about 50%. So at least 50% of this is vapor, the other 50% is not. And inside that, you get more and more vapor. So that's this cavitation pocket. And as they come off of the hammer or out of this cavity, you have these two main regions. And then this bigger region breaks down into two small ones. And now you have very high pressure in these regions. And they break down. And they say that at minimum ring radius and the final stage of the collapse, the pressures generated are in the order of 100 bar. And this high pressure obviously stuns the prey. Now, 100 bar, 100 megapascals, to give you an idea, the tensile strength of aluminium is about 11 megapascals. This is 100 megapascals. Now, obviously, they're not the same thing, but this is just to give you an idea of the force and the pressure we're dealing with. The tensile strength of mild steel is around 200, 250 megapascals, so it's not that high, but it's more than enough to overcome aluminium if you apply it correctly. And they say that as you have C1 and C2 coming off of the hammer, as I said, they break down. C1 is the one that breaks down into two small ones. So obviously this region here is too large to sustain itself, and it has to break down into two small ones in order to, in fact, it actually grows a little bit from the initial time step going to the third time step. It goes through a smaller phase and then a bigger phase. Now, before we go any further, I just want to say, check out our courses that we do here. So if you can get better at theory, like what we're looking at here now, or CFD, which is also this CFD, or experimental. You can take our courses and get better. So you can show all your friends who's the best aerodynamics and who doesn't want that. So let's move on. And they say that in nature, obviously you don't get identical structures. So every pistol shrimp is going to be slightly different. And that means the claw size is going to be different, the closure speed is going to be different, the size of the cavity inside the claw is going to be different, the hammer is going to be different, how much volume you have left once the hammer takes up that space in the cavity is going to be different. And that's going to have a different effect on the jet that you have, the roll up of this vortex, and then the final pressure that you get. So to look at that, they did a parametric investigation where they looked at different closure speeds of the hammer with time. Obviously, with time, it takes more time to go. So in figure 6, they compare the velocity magnitude coming out with closure speeds of 0.3, 0.4, and 0.5 milliseconds. And you can see that as you have a faster closure speed, the jet is higher, the jet speed is faster, which is to be expected. And that also comes with a higher vapor volume, which also then will result in a greater pressure. So the faster you can close that claw, the more pressure you can generate and then stun your prey easier. And they say, indeed, during the last stages of the plunger closure, the depressurization-induced cavitation occurs between the socket plunger due to the expelled jet inertia. Thus, shortly after jet formation, flow rushes back at the cavity formed between the plunger and the socket. So that's another little mechanism that happens. And then in figure 7, as I mentioned, they just showed the amount of vapor volume there. And then in figure 8, they have a really cool figure which shows the pressure being developed with time. And you can see that as the initial, let me zoom up a bit. As you can see at the first stage, you have a very high volume of vaporization, so the cavitation. And as that cavity bubble breaks down, that's where you get that high pressure forming, as we've been saying. So this just proves it here with this nice figure here. And they have pressures up to 200 million pascals. So that's quite amazing. So summing up, they say that the main mechanism of the cavitating claw operation is vortex roll-up. So the vortex ring occurs, and then this is induced by the high-speed gel expulsion from the socket. Depending on the plunger closure speed, the circulation of the vortex ring may become high enough to cause a considerable pressure drop inside the vortex core. Note you need to have a high enough pressure to have a vaporization being induced, so the liquid becomes vaporized. That then leads to a cavity forming, and then you get that cavity breaking down, collapsing on itself, increasing the pressure. And that's how the pistol shrimp stuns its prey. So that's pretty cool. I don't know of any other animal that can shoot anything. If you know, let me know in the comments. I'll be interested to find out. That's it for this video. Do us a favor and hit the like button. Do yourself a favor and hit the subscribe button. And do your friends a favor by sharing this with them. Win-win-win. If you have an aerodynamics problem you need solving, get in touch with us. We'll be happy to discuss what you need and how we can help. Our website is in the description. Also, check out the instrumentation we do at Aerodynamics, and check out the CFD, experimental, and theory courses we do here. Links in the description. Peace out, amigos.